Hello everyone, it's Essen, and this is continuation to my previous video in which I discussed the generation of FIL block, this block right here for the example that was given to us by the MATLAB. And within this presentation video, I would be discussing the application that we designed for the or FPGA loop application that we designed for our Capstone project. And for that, we primarily use two topologies as I discussed in this poster presentation slide, which I will also dive into detail later on. But for this video, I would be focusing on the actual FIL setup or FPGA loop setup for the non-isolated ideal bidirectional DC to DC converter, which is on the top right corner right here. Right, so I will discuss this image rather in detail later on, but let me just dive into the simulation for now. So what you're seeing on the screen is um, non-isolated ideal non-isolated ideal bidirectional DC to DC converter. Um, so it is non-isolated because there is no transformer involved primarily, and secondly, it is non-ideal. Sorry, I said ideal, but it is non-ideal since we are using the ESR and the ESL, or the equivalent series resistance and inductance for the capacitive and reactive elements of the of this converter. Right, so it's a usual bidirectional DC-DC converter in which we have battery on the right hand side with the motor load on the left hand side, and it should also be noted. And we have the motor load on the left hand side, and there are two loads because we basically wants to see the controller response for variational load. So for that purpose, I have used two different load, um, and the load variation is around 50% for this case, and this block right here allows us to change the load during the runtime at the interval of 0.03 second. So this is the converter right here, and with corresponding to that we have the controller, which I will also discuss. But first let me just highlight these two gates that we have, gate pulses that we are inputting into the MOSFET, this MOSFET right here and this MOSFET right here. So during the buck mode, this MOSFET would be off, and this MOSFET would be on, acting as a switch, and the opposite will happen in the boost mode. And simply we have the input filter capacitance and output filter capacitance right here, and simply the and this battery source that you are seeing here is for the buck mode, where we want to recharge the battery. But since this complete test case is in boost mode, so we would only be looking at the load variation, and this voltage source right here would stay isolated or would not be connected. So this is designed on the condition, converter is designed on the is a basically a 20 kilowatt non-ideal non-isolated converter, and that with the input voltage of roughly around 288 volt, and output voltage is expected to be 450 volts. Right, and with corresponding to these load, the output voltage of 450 volt would be maintained using this design controller right here. Right, so this controller right here would be running on the FPGA. This part especially right here, the rest of these blocks that you are seeing are simply the data transitional block and the data conversion block from the double data type to single data type, because this MATLAB simulation environment is running in the 8 byte, while the JTAG interface that we are using allows a bus width of only 32 bits or 4 bytes. Right, so these blocks right here helps us achieve compatibility of the interface between the FPGA block, which would be this one right here, and the actual simulation environment. And these are the mode selection for the buck and boost mode, and similarly we have the generated corresponding output pulse that is coming from the FPGA and would be fed into the simulation environment here. Right, so this part right here of the converter simulation would be running in the simulink environment, whereas the data would be taken using these blocks right here to and from, and would be sent towards the FPGA in this block right here, FIL block, and it would be processed on the FPGA to the controller would be running on the FPGA and will process the corresponding duty cycle in order to generate the gate pulses for both of the MOSFETs. Right, so so this block right here was HDL designed to be an HDL compatible, and corresponding to this block we generated an FIL block which can be run in loop with the FPGA. But since I don't have the FPGA at the moment, I would simply show you the result from the from the HTL block compatible block within the simulation environment, and similar to that we would have the results within the FIL setup as well. So for this closed loop control, this entire controller is HTL compatible. We have the separately designed PI controller for the post mode as well as the buck mode. We have the reference voltages and then the actual output voltage for the post mode and buck mode. For the boost mode, the actual output voltage would be of the motor load, and for the buck mode, the actual output voltage would be of the battery. And corresponding to that, we input the reference voltages, and corresponding to the mode selected, this switch right here decides whether we are generating the duty cycle or calculating duty cycle for the boost mode or the buck mode. And then we have the duty cycle generator, which is designed using discrete components using a simple HTL counter right here, and corresponding to that we generate a pulse which is then inverted for one of the gates and is fed as it is into the other one. So this entire part is HTL compatible. So once we have a designed HTL compatible controller, the next step was to generate FIL compatible block, which was performed done using the steps that I explained in the previous video, which you can see on my YouTube channel. And then we would simply run the simulation to see how the results goes. Right, so on the screen we have on the top left corner we have the battery parameters. The first one is the state of charge. So battery is initially charged at 90% state of charge, and then it is decreasing, and exactly at the 0.03 seconds where the load variation of 50% occurs, the slope of the state of charge decreases since now the load is drawing lesser current compared to before. So there is change of slope that can be observed within the after the 0.03 second. It should also be noted that it is working in the boost mode, so the battery is discharging. And similarly, we can observe the variation in battery current since load is decreased, hence the current drawn from the battery has also decreased, and the voltage roughly remains the same. On the bottom left corner we have the motor load, which tells us the load current and load voltage. So the load voltage, since I said the design controller is supposed to maintain the output load voltage of 450 volts, so that it is doing with a little bit of a undershoot and overshoots that can be observed, settling time of 0.01 second roughly. And then we have variations as well. So the steady state error is roughly around 0. So the parameters of these parameters, rise time, peak time, settling time, and overshoot and steady state error are discussed in detail in my thesis. So if you want to go through that, you're free to do so. So the voltage is maintained, but the load current can be observed to decrease since at 0.03% we have 50% load variation. So the load current can be seen to be decreased from 45 to 30 amperes. Right, and on the top right corner we have the gate pulses. If I just zoom that in, you would be able to get a better view. Right, you can see the gate pulses are exact inversion of each other, just because we are performing synchronous rectification where we give the pulses to both of the MOSFET rather than just acting one of the MOSFET as diode. So since we are performing synchronous rectification, so the pulses would be exactly inverted, which can be observed in this plot right here, where one gate pulse when is 1, the corresponding for the corresponding time period the gate pulse 2 would be 0, and so on. And finally we have the inductor, the converter's inductor behavior, which is plot in order to verify our calculations. It can be seen that inductor voltage gives the ideal value as well as the inductor current as per our calculation. Right, so I won't be diving into the detailed calculation or mathematical calculation that we performed for the designing of this converter. That too again is present in our thesis, and you can go through the detailed mathematical work in order to verify these values that we are obtaining right here for the inductor and the inductor current and voltage yourself. It's just that here we can verify the graph as it should look like and the way it is looking as of now. Right, so these are the results for the first test case, which was the load variation, where we changed the load from 50% to decreased the load to 50%, and the Second test case that we can perform is the variation from the boost mode to buck mode. For that purpose, I would simply replace this particular block with the mode selection block. Right, so for this test case, we will start with the boost mode, which is represented by 1 right here at the time interval of 0, and all the way till 0.03 second we would be running in the boost mode, after which we would switch into buck mode, and again at 0.05 second we would switch back to boost mode. So in the boost mode, the battery would be discharging, and in the buck mode, the battery would be charging, and we would see that shortly in the results as well. So let me just write. Let us run this. Right, as you can see on the screen, for the battery state of charge decreases from 90 up to 89.994. So the small decrement is primarily due to the fact that the battery capacity was kept to be very high, which as we can see here um, is around 90 ampere hour, which is sufficiently large capacity. So that's why there is this slight only slight decrease in the state of charge in the boost mode. And as soon as we enter the buck mode, we again then start charging the battery, and this case can be considered for the regenerative braking of the electric vehicle. And again after 0.05 second we start discharging, because we are again in the boost mode. Right, and similarly corresponding to that, the current can be observed as well, since the battery is discharging during the boost mode, so the current is positive, and when the battery charges, the current is observed to be negative, and then the same things happens as well as with the voltage. And as far as the load voltage goes, we have observed the similar behavior as before for the boost mode, and as soon as we enter into buck mode right here, so we obtain this straight line at 450 volts, which is the desired output voltage. So the reason why there are no variations within this buck mode is because we are using an ideal voltage source right here of 450 volts, which gives us this steady state voltage during the buck mode at the output. And then again when we transition to boost mode, we can observe these variation in the output load voltage. So these overshoot these parameters of rise time, settling time are basically tuned using the PI controller right here, which I discussed as well. So I just want to mention one thing regarding these PI controllers. So the gains for these PI controllers were calculated using the Zeiger-Nichols method, which utilizes the transfer function of the plant in order to calculate in order to tune the PI parameters. Right, and similar to that, we have the gate pulses with similar behavior of synchronous rectification that I explained before. So if we could just zoom in at this interval where we are switching from boost to buck mode at 0.03 seconds, you can observe that right here there is this gap where there's this gap where what happens is that since we when we are in boost mode, so the pulse is the primary pulse is for the is the gate pulse 1, which is corresponding to which the NOT gate inverted pulse gate pulse 2 is generated. Whereas in buck mode, the primary pulse that is generated is the gate pulse 2, and inversion of that gives us the gate pulse 1. So so this behavior can be observed right here at 0.03 second where the transition occurs. And similarly, we have the inductor behavior right here, which again is only in order to verify the mathematical modeling that we did, or the experimental calculations for the values of inductor, capacitor, of the input output current, of the load that we did for this test case. Right, so these are the results as far as this non-isolated non-ideal bidirectional DC-DC converter is concerned, with its STL compatible PI controller. And again, if you have an FPGA, you can simply use this simulation and just load this bit stream file generated right here in this folder on the FPGA, and then run this control on the FPGA. For that purpose, you will simply have to comment this out and have to reconnect this block with these two gate pulses right here. Right. So this is it as far as the study of of the the non-ideal, non-isolated bidirectional DC-DC converter goes. And again, this was designed in the context of electric vehicle. That's why you see the um, high power rating of 20 kilowatt. Although ideally you don't have non-isolated converters operating at this much of a power rating, but since it was designed in context of electric vehicle, so we had to tune up some of these parameters. Right. So I think this is it as far as the study for this case goes, or for this top right setup goes. And in the next video I would be primarily targeting the study of this isolated converter, which is an ideal which is designed on an ideal plant, and its FIL setup as well, and we will then discuss its result in detail. And then finally I would also make a separate video about, or the same video, within the same video we would look at these mathematical models as well. Or we can just simply so these mathematical models, this one right here for the non-ideal, non-isolated bidirectional converter, we derive these mathematical models since our control parameters for duty cycles. So we derived our mathematical model using state space averaging, and then performing the small signal modeling, and then finding the state space variables, and then using the transfer function identity, which I have discussed rather in detail in the thesis. We obtain these transfer function of the output voltage, steady state output voltage, output voltage with respect to the variation in the duty cycle for both the boost mode as well as the buck mode, which can be seen here. Right, for this case, non-ideal, non-isolated bidirectional. So this is for the boost mode, this is for the buck mode, and with this corresponding transfer function, we simply obtain the PI gains that we need for our controller, and then once we had these PI gains, we then this was the setup that we kept in order to perform the experiment. So we had this non-ideal bidirectional non-isolated DC-DC converter, and then we have the FPGA in loop setup, which, since we are using Zinc FPGA, Zinc 7000 system on chip on that board. So this one is right here, and on this Z board we have two controllers primarily running. The first one is for the buck mode, and the second one is for the boost mode. And then we have the charging discharging controller using the which decides which pulse to be forwarded. And then in between these we have data type convergence and data transitional blocks within the simulation environment. Right. And similarly for the results, as we discussed, these were the results for the 20 kilowatt non-ideal, non-isolated bidirectional DC converter. The first results that we discussed were the case of load variation 50%, which were these ones on the top right corner. And then we, for the bidirectional mode in charging and discharging, or motor load and degenerative braking in the buck and boost mode, we had these top left results right here. Right. I think this is it for the video of the non-ideal, non-isolated bidirectional DC-DC converter and its STL compatible controller. And in the next video we would be looking at the other case, right? So if you have any question regarding this setup or this video, please do let me know by email, or just comment it down below, and you can find the files using the link below, right? So I would see you in the next video. Thank you, and Khuda Hafiz.